So thank you for the introduction. I'm a PhD student at the University of California, Santa Barbara in the physics department, and I'm being advised by Deborah Feigenson. And today I'm going to speak to you all about how I've performed precision measurements of DNA Nanostar Phase Diagrams and revealed some very unexpected salt effects. So we're going to start by justifying this as a precision measurement, in that we are measuring DNA Nanostar condensate volume fractions. From there, we're going to show you high-resolution phase diagrams of a 3R nanostar. And finally, we're going to explain some counterintuitive features. A nanostar schema would be useful. These are three rationally designed oligonucleotides that we anneal together to form this complex macrostructure. You'll notice that there's two single-stranded nucleotides at the junction of each monomer, on the junction of each strand. And you'll also notice that there's a palindromic overhang attached to a free nucleotide, such that this actual overhang is free to rotate. And we do this such that at temperatures beneath the upper critical solution temperature, we can see a monodisperse emulsion phase transition into a heterogeneous one of a dense and dilute phase. You can see it depicted here in this little cartoon. And if we use the phi symbol to represent volume fraction, with a filled-in bullet or an open circle to represent dense and dilute phase respectively, we're going to make a couple assumptions. Let's say that the nanostars are an incompressible fluid. We should be able to write the conservation of mass in terms of the actual concentrations themselves. And we're going to assume that the Debye length and the temperature are the two thermodynamic variables that are governing the phase concentrations in equilibrium, namely not the amount of nanostars in the system. From there, we get away with fitting a linear regression if we measure the volume fraction of condensate at various concentrations. We're able to measure a slope and a y-intercept, and from there we have all of the information we need to calculate the phase concentrations themselves. So how is this a precision measurement? I've engineered and exploited droplet microfluidics, which you can see in the top right corner, to produce monodispersed condensates with respect to concentration and volume. And the overall concentrations we're typically looking at are beyond order 1 in 120 micromolar. The first thing that we would do, by the way, these are also imaged under fluorescence, which is an important detail, right? So the first thing we did is we used the machine learning program to identify the centers of mass of every condensate in every image at every temperature. Then we needed to find the outer radius, but I really didn't want to go through the headache of using a higher order functional form. So instead, we simply inflated circles around each of these centers of mass until they made contact. At that point, the algorithm was terminated, and we directly made a measurement of the outer radius due to the sphere packing geometry that microfluidics permits. We then measured the point spread function under the emission of psi3, which is the fluorophore we're using. And we fit a double sphere function, knowing this radius, and convolved it with the point spread of the objective and chose the fit with the lowest residual. That gave us an accurate measurement of condensate radius. From there, of course, we were able to compute a volume fraction, and due to the large number of emulsions within each sample, we got away with using the standard error to report the error in our volume fraction. And then we performed a least squared linear fit. For example, this data was taken at 18 degrees Celsius and an ionic strength of 150 millimolar, and to me, that looks fairly linear. And indeed, you'll notice that the colors of the dots correspond to the raw data you are actually looking at the moment. So, let's show you some of these highly resolved in temperature phase diagrams. And here it is. Each of these 2 points at each temperature come from an individual lever rule calculation, measured under what I call an adiabatic ramp protocol. As such, let's take a look at some inconsistencies. We measured the actual transition temperatures at which concentrations went from a heterogeneous system to being just a homogeneous suspension. And we're able to see that this lever rule model seems to be over-predicting the dilute phase concentration, as the small concentrations are melting at temperatures that are higher than that the curve would predict. Just so you all know, these black and blue points should be completely continuous with each other. We also have reason to suspect that the high concentration or emulsions are transitioning at temperatures lower than what we should think. And on top of that, you've probably noticed that on both the standard plot and the log plot, the actual evolution of the condensate concentration is non-monotonic, as well as the dilute phase as we increase the temperature. And I don't believe it, because at low temperature, we see error bars at 18 Celsius of about 30 micromolar. And this is quite literally doubled by the time we get to high temperature. Given the fact that this was a precision measurement, we had a boatload of data. We decided to actually look at the volume fractions at every single temperature for each of these 10 samples. those small and homogeneous concentration monotonically decreased to a volume fraction of 0. However, you'll notice that the largest concentrations, in fact, increased their volume fraction until hitting some terminal value that we will call a terminal volume fraction. At that point, the emulsion transitioned into a homogeneous phase, but the point is, we never saw volume fractions approach 1. So we knew something was up, and if the lever rule is a linear scaling relationship, we should be able to use the chi-square to determine the degree of linearity. Take, for example, 20 Celsius. That's here on the phase diagram. And we see a chi-square of about 1, so we're getting away with this model. By the time we get to 32 Celsius, we see a chi-square of 2, so there's really a poor indicator of linearity, and I don't think anybody would argue that this function is linear whatsoever by the time we get to 36.5 Celsius. Since we had 10 different concentrations that we were using to fit this model, we decided to use subsets of our data to see if we could reproduce the same curve. And you'll see that when we looked at the 5 highest concentrations, we produced a dense phase that was 50 micromolar lower. And on top of that, there's significantly more curvature and overall convergence to this binodal. We then looked at an intermediate range of concentrations, and we saw that the dense phase increased slightly, but there's less of a change to the dense phase and dilute phase as you go up in temperature. And by the time we looked at the smallest concentrations, we saw that the dense phase was safely outside of error bars from the other samples. To give you an idea, these are the 3 different diagrams we were measuring. This is disturbing. We're using a linear model to measure phase concentrations, and yet we're getting completely different curves depending on what samples I happen to be looking at. And funny enough, the actual quality of fit with 5 points is fairly decent up until about 2 degrees of the melting temperature. So what's going on here? Well, perhaps nanostars themselves are being affected by the solution in some way, and what could possibly be responsible for this? Well, maybe the solution to our problem is, funny enough, the solution, and by that I mean salt. When you think about the nanostar itself, it's comprised with 147 phosphate groups, each of a charge -1. It seems reasonable to claim that somewhere between 1 and 147 counter ions will be adsorbed onto the surface of the backbone. To give a back-of-the-envelope intuition, that could perturb the salinity of a high concentration system by up to 20 millimolar. And so we decided to lower the salt. If this is going on, let's make the effect worse, right? So we went down to 300 millimolar and 150 millimolar. And the first thing we noticed is that the dense phase concentration indeed does decrease as you go down in salt. And we've also saw a suppression in the amount of temperatures that our system is able to be heterogeneous within. But as you look at these transition measurements where we melted the emulsions, these concentrations of nanostar themselves are roughly identical. And yet the slope of these melting points is very different as we go down to a low salt environment. So we decided to look at our well-resolved volume fraction movies. And of course we saw that the less concentrated condensate at low salt corresponded to a higher terminal volume fraction. And I know this might be hard to read, but I promise you that within error bars, these 2 highest concentrations are identical. So let's take a look at what's actually going on in this specific movie over this specific temperature range. You'll see that we have an emulsion that is in a stable heterogeneous configuration. And yet as I increase the temperature over about 1 degree Celsius, we watch this volume fraction simply disappear. It never swelled to a volume fraction of 1. It simply just dissolved to a homogeneous phase. I'll show you one more time, just for clarity. So here's where I pitch my hypothesis. This charge adsorption is lowering the effective salinity of the solution. And this is being done in proportion to the amount of nanostars that I happen to suspend in my encapsulations. This would change the compressibility of the individual nanostars. And why do I say that? We ran some basic oxDNA simulations on the nanostar that we've been talking about herein. And we saw that under different salt conditions, namely about 500 millimolar and 100 millimolar, there are completely different geometries to these nanostars depending on their screening environment. And to make this point a little bit more clear, because it's very difficult to see on this scale, let's zoom in at the junction. And we see that under high salt, which to put some numbers on this, corresponds to a Debye length of about 6 angstroms, versus 9 in the low salt. When we're at high salt, the phosphates on that single strand are adequately screened by the solution, and as such, the pi bonds of the nucleotides are able to overlap. This confines some of the entropy to the overall structure. And yet in the low salt environment, as these nucleotides are able to sense each other and are not being fully screened, these nucleotides swing out of the junction, the pi bond stacking is no longer happening, and we have increased entropy to our monomers. What's the result of this? Well, we've already said that at low temperature, we're able to get a linear scaling relationship between volume fraction and concentration. This is likely due to the fact that the hybridization interactions are very strong in the system at low temperature. And we don't really see these minor differences in flexibility manifest in the scaling relationship. But as we hamper the ability for the sticky ends to hybridize transiently, as we go up in temperature, these finite differences to the entropy of the monomer begin to matter more and more. And the lever rule as a model completely breaks down. These forbidden volume fractions that we've seen, or terminal ones as I've introduced them to you, likely arise as a result of the entropy of the monomer being too high to justify the energetic cost of forming a highly dense condensate. And for completeness, these three well-resolved phase diagrams are presented on the same axis over here, just because I think it's a very pretty plot personally. So the takeaways. We've shown that droplet microfluidics has enabled a precision measurement of nanostar condensate volume fractions. We've shown that these phase concentrations are functions of the actual concentration of nanostar you happen to be looking at. And finally, we've shown that terminal volume fractions can be plausibly explained by salinity-dependent entropy of the nanostar monomers themselves. I'd like to take a minute to thank my two very talented undergraduates, Nick and David Ewert, both of which are going to matriculate to grad school in the fall. I'd like to thank Connor Chatfield, my dear friend and colleague, as well as Phil Pincus, a great professor at UC Santa Barbara, for the discussions and elucidating some of the subtleties we saw. Last of all, I'd like to thank my doctoral advisor, Deborah, for the intellectual sparring sessions, fighting me back and pushing me to try and get this precision measurement to work in the first place. I'd also like to thank our funders at Sloan and the NSF, and if you would like this slide deck, feel free to take it. And I'd now like to open the room to questions. Thank you.
Time for one quick question while the next speaker gets ready.
Yes.
It's maybe not super simply, but how confident are you that some of the dilute phase you see is actually fully formed stars that are in dilute phase rather than kind of half formed or maybe truncated versions, because this DNA, a lot of it is going to be truncated or a bit wrong?
That is no doubt a thing. In fact, one of the things that I would like to look into next is the difference in purification methods between the strands that we're ordering, because no doubt you're right. However, I would tell you that our actual nanostars themselves are manufactured with their sticky ends first, which is the most important ingredient. So the probability of an issue on that sequence is relatively low. As far as I know why the stars are annealed, it's because, well, yes, these salt perturbations are going on between the two phases. It's really not much, right? In fact, when I go and I get these concentration measurements, I intentionally knock down the salinity of the solution by a factor of 100, such that the nanostar structure itself is unstable, and I can just measure raw oligo strands instead of this macromolecular structure. So while no doubt there may be some moieties here and there, I'm not particularly concerned about that many differences in the structure of the stars, because we've used HPLC purification, and they have some really great standards on the actual sequences.
All right, let's thank our speaker one more time.